Hello, I'm Keisuke Harigaya. So today I'd like to introduce my work with Nima Alkani-Hamido on the muon G-2. So here's a plan of the presentation. So I first briefly introduce what the G-2 is and some experimental status. So then I will introduce a natural model to explain the observed discrepancy between the observed G-2 and standard prediction. Natural in a sense that there is no hierarchy problem beyond that of the standard model Higgs. So I use natural model, but I will then explain that the model predicts unnatural G-2, unnatural in a sense that the naively expected leading contribution to the G-2 actually vanishes, unnaturally vanishes. So I elaborate on this surprise in the effective field theory point of view. So then I then show the actual leading contribution to the G-2, and then just briefly discuss the implication to phenomenology. Okay, let's start from the brief introduction to G-2. G-2. G-2 is basically a coupling between a G-2 of a particle is a coupling between its spin and the magnetic field. So m is the mass of the particle, g is the constant, spin, times magnetic field. So this is G-2. So at the three level, or I can say that from the Dirac equation, we can show that this G equal 2 for charge 1 spin half fermion. Now, however, this receives quantum correction, and the correction to the G from the 2 is called G-2, or called anomalous magnetic moment. So we quite often use this kind of notation, A, anomalous magnetic moment. So we can, of course, compute this within the standard model framework, say QED correction, say for 5 loop, or electroweak correction, or QCD correction. This doesn't occur at the leading order, but to this photon loop, we can add some quarks, add the loop from the quarks. So, for example, the electromagnetic contribution is as large as 10 to the minus 9. So the experiment in the Brookhaven was conducted with a sensitivity that can check this standard model electroweak contribution. But however, it found that for the experimental value larger than the standard prediction by roughly 10 to minus 9, with an error smaller than by a factor of 4 for in comparison with this discrepancy. So this may be due to some uncertainty in the standard prediction. So for example, the largest uncertainty comes from the QCD contribution. So people basically try to compute this QCD contribution that is, of course, non-perturbative in 2 ways. One is using the data. We can, for example, we can compute the electron-positron annihilation into hadrons. And based on this data, using dispersion relation, we can compute the QCD correction to the G-2. When people say, oh, there's discrepancy, that is based on this computation method. But it maybe should fair to mention that there's another computation using, of course, lattice simulation. that is basically consistent with this estimation based on the data. But however, the most recent one seems to suggest that this discrepancy may actually vanish if that computation is correct. Now that's the present status. But however, today I would like to believe this data-driven method and would like to try this observed discrepancy by new physics models. Yeah, W0, yeah. So then, yeah, this one loop gives this result. There's basically no uncertainty from the electric contribution or QED contribution. So, and then this discrepancy was also confirmed by another experiment at the Fermi Lab recently. Maybe you heard about the news recently, few months ago. So people are excited about that. So new physics. So almost all the model has a following structure. So we have some left-handed muon, and we have right-handed muon, and there's some loop to which the photon is attached, and to preserve the electric symmetry, which is also attached Higgs. So almost all models consider this type of quantum correction from new physics. So one example which gives this effective dimension 6 operator. Oh. So that's what we do. And you can see that you can.
Does this diagram lead also to mu to E gamma?
So if this is yes, there is some flavor changing process. Yes. So in general, we should be careful not to introduce mu E gamma because there is a strong constraint on that. So typically, we need a suppression of 10 to minus 4 to 10 to minus 5 in the mu E gamma matrix element in comparison with the matrix element to explain the muon G minus 2 discrepancy in the muon G minus 2. We should basically consider a theory where lepton flavor number is preserved.
But can you do mu?
So actually, this is lepton doublet. This is L. L. That is this is doublet muon.
Mu.
Yes, mu. Yeah.
Okay, that's not.
This is L. Yeah. Today, no electron appears. Always, this is always muon. So this is always muon. Yeah. They are different operator, but they both give G minus 2. Yeah. Sorry. Let's see. Related by the. Even after using equation motion, we have some residual term proportional to the mu mass square. So they are not the same operator. But the same with respect to G minus 2. The easiest way to see that what your relation is, this is, yeah, as you say, this plus this, and this using equation motion, this is muon mass square. So they're equivalent up to this term. Sorry. But without looking at the detailed model, we can extract, we can give a naive expectation for the new physics mass scale because after you remove that photon, this diagram becomes the quantum correction to the muon-Yukawa coupling. So this anomalous magnetic moment from the dimensional analysis roughly is given by this relation. So here, delta times mu is a quantum correction to the muon mass when we remove the photon. So this m is a mass scale because we have square because muon mass comes from dimension 4 operator, but G mass comes from dimension 6 operator. And this m mu comes from just from definition of the muon G minus 2. So if, for example, if this quantum correction to the muon mass is a part of the quantum correction proportional to the muon mass, so up to coupling constant, we will have this. And the expected new physics mass scale is around 100 GeV scale. Yes, so this is the yes, in addition to the 3-level muon-Yukawa. So we have three-level one. Yes. Yeah. You may also consider theory where muon mass, this quantum correction actually dominates the muon mass. So in this case, from this number 10 to the minus 9 and the muon mass 0.1 GeV, the naive expected mass scale is TeV scale. So based on the naive estimation. But I should tell you at this point that this naive expectation fails unnaturally in the model I present today. So you see some familiar number, electric scale, or some scale a little bit larger than the electric scales. So people typically associate this observation or coincidence with the expectation that maybe behind the muon G minus 2, there's a new physics that is connected with the origin of the electric scale. That is also around the 100 GeV scale. So that's the conventional idea on the new physics explanation of the muon G minus 2 for the last 10 years. But recently, the situation has been a little bit changed. As you may have heard, so LHC so far have not yet found some new physics that will be responsible for the origin of the electric scale. So for example, so maybe you have heard about the supersymmetric theory, where the Higgs quantum correction to the Higgs mass is cancelled by Suji particles. So in that kind of theory, we should have a top partner around the electric scale. But however, recent LHC constraints show that there should not be such top partner below the TeV scale. So based on this situation, it may be a time to seriously consider the possibility that electric scale is simply a fine-tuned parameter, and the Higgs mass is really just fine-tuned parameter, maybe for some anthropic reason. And the cutoff scale of the standard model, such as a Suji mass scale, is much higher than the electric scales. So one interesting theory is the theory, the supersymmetric theory, where cutoff scale or Suji scale is around 100 to 1000 TeV scale. And the electric scale is, of course, around 100 GeV. So this kind of hierarchy is called a little hierarchy. So you may think that this is not so good, but there is some advantage behind this kind of setup. So for example, since the new physics scale is high, so there is no problem of the CP vibration or a flavor vibration arising from the quantum correction by the supersymmetric particle. Or so this we can compute the Higgs mass based on this scenario. We can show that Higgs mass is actually consistent with observed one, 125 GeV. Or we have some cosmological advantage. So I would say that the model with large cutoff is also interesting. But if this kind of theory, the theory where standard model cutoff is high, what is the natural way to explain the muon observed discrepancy of the muon G-2? So obviously, we should not use a new scalar particle because scalar particle should have a large mass, much larger than TeV scale, so that its contribution to the G-2 is negligible. So today I'd like to consider the new physics where the only standard model particles and new fermion explain this discrepancy of the G-2 because the fermion mass is stable against quantum correction. So that even if the cutoff scale is high, low scale fermion mass is natural. So you'd like to consider such a natural model. They may have super partner that is scalar, but so they're not super partner of the standard model particles. They're completely new particles. Yeah. So that model, I see a model. So in order to utilize them, we need some super scalar partner of fermion. Whose mass scale is maybe is huge, so they do not contribute to the G-2. So maybe I can show explicitly. So to write that, we need. So this is Higgs, So then we always need this scalar partner of them. So Higgs, Yeah. So this is negligible. Yeah. So okay, let us consider minimalistically. We have standard model, and the minimal possibility is to introduce a vector-like fermion that has the same charge as the standard model lepton doublet and singlet. That's all. We only introduce two fields and introduce a possible Yukawa coupling. Standard lepton doublet, singlet, Higgs, and the mu. Okay, Higgs. So this is the interaction of those new fermion with standard particles. We can also write down the interaction among the new particles. So this is all possible Yukawa interaction. So here I impose some lepton symmetry so that there's no Yukawa interaction such as LS with that conjugate. Because if we have that, we have lepton number vibration, and we have too large quantum correction to the standard neutrino mass. So we should consider the theory where lepton number is imposed. So you may think that, this theory should readily explain the muon G-2. In fact, we can write down some Feynman diagrams that seems to generate muon G-2. For example, you can easily write down okay, so you can write down these diagrams. So this chiarity is actually flipped. So this should correspond to this muon G-minus operator. So if someone asks me what's the naive expectation of the size of muon G-2, I would immediately say that, oh, of course, muon G-2 is one loop suppression, and those Yukawa coupling square, and the mass of new particles, and let's see, like this. But it turns out that this is completely wrong. So this naive expectation is wrong. So I'd like to show that. In most of my talk, I never actually complete Feynman diagram. I just show the result based on dimensional analysis. But today I have to make exception because this naive dimensional analysis is completely wrong. So after, then I would like to explain why this G-2 that seems to exist actually vanishes. The computation itself is quite interesting, and I would like to take some time to explain that in detail. So then I would again explain how unnatural it is from the EFT point of view. Okay, computation. Sorry?
If it did not vanish, what order of magnitude would it be?
So it
would assume y is over 1?
Yeah. This coefficient would be naively order 1. And we can easily explain the muon G-2, even if the new fixed mass scale is as large as the TB scale. But the phenomenological implication is because of if reading correction vanishes, the required mass scale is lower, so that that model is more easily experimentally accessible. Yeah. I will later show some phenomenological implication behind this blackboard. Okay, so anyway, let's compute. Now let us first compute the contribution proportional to these two Yukawa interaction and this first Yukawa interaction among the new particles. So since this is a neutral particle, so we should attach a photon here to the charge Higgs line. So this is the Feynman diagram. From this diagram, you can look at the Lorentz structure of the fermion. It just goes straight without any photon attached. So the Lorentz structure should be just the one where this doublet and the singlet indices are contracted straightforwardly. So it should be this operator. rather than this operator. So to compute G minus 2, we should just focus on this operator, whose contribution to the G minus 2 is proportional to extra momentum of the photon. I don't know, extra momentum of the fermion, rather than the extra momentum of photon. So what we can simplify the computation by putting this to be 0 and work linear order in the external momentum of the fermion. Okay, let us write down the integrand. Of course, since the charge Higgs is would be non-Boson boson, its mass vanishes. But for now, I will keep its mass as a free parameter to see how important it is that the charge Higgs mass vanishes to obtain the conclusion that this diagram doesn't contribute to G minus 2. With some, so this part comes from propagator of the Higgs, and this part comes from the propagator of fermion. So, to the leading order in the external momentum, this is proportional to U is a momentum, Euclidean momentum square. So muon G minus 2 should be proportional to this integrand. But however, this charge Higgs is a would-be non-Boson boson, so its mass should vanish. So you can see the correction to the G minus 2 is proportional to the function, the value of the function f at infinity minus that at 0. So this vanishes, as you can see from the function form. It just simply comes from the calculability of the muon G minus 2 in this renormalizable theory. What is surprising is the F0 equal 0. Actually, what's non-trivial is the F0 equal 0. This is not guaranteed from the calculability. It could be non-zero. But the reason why this function f vanishes at 0 is simply comes from this structure of the propagator. That okay. So with that chiarity flipping, it is proportional to that's this, and with that vanishes. So this comes from the absence of the chiarity flip. But we can see that this F0 should be 0 in a different way and a more interesting way. So when this momentum goes to 0, we should be able to understand that integrand based on the coefficient of the possible effective operator involving this field without any derivative. But however, in what we can write down is so based on the SU2 symmetry. So this is the operator that is available. So based on the SU2 symmetry and the structure of the SU2 index here. This SU2 index should be contracted with the SU2 index here. But however, this SU2 index should be contracted between these Higgs and these Higgs. So this identically vanishes. So this is another way to see that the function f vanishes at 0. So here you can see that it is crucial that we only utilize the standard model Higgs rather than some new scalar to obtain the conclusion that the muon G minus 2 vanishes at the leading order. One comes from this mass here. If these particles are new particles and has non-zero mass, muon G minus 2 actually non-vanishes. Two, if this new particle, this is a new particle, if this and this may be a different particle, so that this SU2 doesn't tell us that this identically vanishes. So this is a crucial consequence of the assumption of no scalar beyond the standard model Higgs. So interestingly, this natural model, because of its naturalness, is quite unnatural. Okay, so let us now also check another diagram using this operator, this interaction, this one. So for that contribution, we must be a little bit more careful. So we can write down this diagram. So in this case, we can write down two diagrams, and we should sum over them. But you can again find that muon G minus 2 is proportional to the same integrand. And again, muon G minus 2 vanishes. But here, you can see the power of this SU2 argument. So because we have some chirality flip, so we cannot say that based on just simply by looking at the structure of fermion propagator, the function should vanish at the origin, and a G minus 2 should vanish. But however, we can instead use this effective operator argument in the limit where momentum vanishes. This part should be expressed by a higher dimensional operator. And the unique possibility is this, which again vanishes because of this SU2 gauge symmetry. You can see that here is really crucial that we only have a Higgs as a scalar particle inside the loop. So I'd like to now elaborate how surprising this is to me using the EFT point of view. As I told you, the G minus 2 is proportional to this total derivative, which trivially vanishes. But this looks a little bit more interesting if we actually look into the integrand. So this is the form of the integrand. So which have just two peaks. So now let's take, for example, take the limit where singlet mass is smaller than a doublet mass. And the two peaks exactly cancel with each other, which is of course guaranteed because this is a total derivative. But however, let us now be ignorant about the UV physics and consider this integrand from the EFT point of view. Now, let us become the EFT theorist with an energy scale much below the new particles. Then that EFT theorist will try to compute or try to estimate the size of the correction to the G minus 2 based on the low energy EFT operator. Actually, we do have a candidate. We have a dimension 8 operator after integrating at both singlet and doublet. We have dimension 8 operator. So from which we may naively expect via the so-called quadratic divergence of then the dimension 6 G minus operator. And that is almost correct. Actually, you can see that starting from this low energy EFT, if you perform integration over momentum, you see the quadratic divergence. And this is kind of similar to the computation of the mass difference between a charged pion and a neutral pion. If we look at the low energy effective field theory, we have a charged pion that couples to a photon. So, and that's quantum correction is quadratically divergent. We naively cut it off at the low mass scale. We have roughly the correct answer. That is what we usually have. That's usually that's a good. That's the success of the EFT. But however, you can see that EFT completely fails for this theory. It is true that we have a quadratic divergence, which seems to generate a muon G minus 2. But if you look at the actual UV physics, this quadratic divergence is cancelled by the UV contribution. So this is like the computing the charge correction of charge pion mass, and by some QCD miracle, you find no correction. Or compute the quantum correction to the Higgs mass from some new particles, and you naively expect the quadratic divergence occur and Higgs mass correction is large, but found that it miraculously cancels. So yeah, this is very interesting to me. So now let us look at another EFT at this energy scale. The energy scale, below the one of the new particles. So for that EFT theorist, so you can compute the correction of the muon G minus 2, and you find that there is IR calculable quantum correction of the muon G minus 2 from this. Then you may again think that, okay, muon G minus 2 should vanish. However, that is exactly cancelled by the UV counter term. So again, the EFT analysis fails here. So this shows that when you consider some phenomenology of the new physics model, you should not always use the naive dimension analysis and the loop counting. You should actually compute that. And you may find some surprise. So, okay, so then I would like to shift to some phenomenology. So then what is the actual prediction of the model? So you may first think, oh, maybe this cancellation, this absence of muon G minus 2 occurs only at the tree level. I don't know, only at the one loop level. We will naturally have a two loop quantum correction. And that is right. Our naturalness expectation actually is successful from the two loop level. So for example, for this diagram, so we can add, before going to that, I should say that, okay, let us try to add quantum correction to this fermion propagator. But however, that does not work because whatever we do to this neutral fermion propagator, you can still use the argument of the SU2 symmetry so that this part should be proportional to effective operator. That identically vanishes. So we should touch other part. So then the leading contribution is the correction to the Higgs propagator. Higgs has an order one coupling to the top quark. So you can add top loop here or here or here. So what happens is that because of the because this is basically the electromagnetic current at low energy limits. So this should not correct the vertex, but this should only correct the work as a wave function normalization of the Higgs. So what happens is this integrand, the total derivative integrand, is corrected by a wave function normalization proportional to the top quark Yukawa plane. And since this is no longer a total derivative, this no longer vanishes. So we obtain non-zero G minus at the two loop level. From the integrand point of view, what happens is this peak and this peak are slightly different from each other by this log factor, log ML and log MS. So we obtain a correction proportional to the log of this. So this is one of the, not leading, the one of the important correction. But another important correction, this correction is still expressed as a dimension 6 operator. We have two fermion, one Higgs, and one photon. But there is actually, what actually is important is dimension 8 operator, where we add two more Higgs to the diagrams. Actually, so here I took the limit where ML is much larger than MS. When ML is close to MS, there still is non-load correction. The G minus still non-vanishes. Yeah. So, okay. We actually have one loop correction to the dimension 8 operator. LH. And we just add two more Higgses. So it turns out that numerically, in the parameter region where muon G minus 2 is explained, this is the dominant one. But of course, this is some numerical things. If the muon G minus, deviation of muon G minus 2 is it's actually is smaller, and the required mass scale is heavier. Since this is dimension 8 operator, and since this is dimension 6 operator, this term actually dominates. But for phenomenologically, this is more important. Okay, so now let me briefly explain the phenomenological implication. How should we test this theory? One is exciting. We just look for these new particles. So this, especially this particle, has a gauge interaction, and that can be produced by the electric interaction from the proton-proton collision, namely at the LSC. Another possibility is you have this diagram of this interaction, which is sizable. After putting Higgs wave, this introduces a mixing between this particle and this particle, namely mixing between neutrino and some singlet particles. So as a result, standard model neutrino is a linear combination of doublet and singlet. So its coupling with electric leakage boson deviates from the standard model prediction. So especially since we only introduced this interaction to the muon or second generation, the universality of the first generation is lost. And the same is also true for this coupling. Now, the standard model right-hand muon is a linear combination of, by the way, a linear combination of the singlet, SU2 singlet, and SU2 doublet. So again, the coupling of the right-handed muon with the Z or W boson deviate from the standard prediction. And also, as I explained, if we detach photon from this diagram, this gives a quantum correction to the muon mass. So we do not want the quantum correction to be much larger than the muon mass, because if that's the case, we need some fine-tuning between a trivial contribution and this quantum correction. So this is the constraint on the model where, which one? The model where we introduce, yeah, one of those coupling. Where we introduce okay, this coupling LS. The other one is similar. So x-axis is the mass of this doublet new fermion. Y-axis is the mass of the new singlet. So below the ML, below 600 GeV, is already excluded by the LHC search for these new particles. And above this dashed line provides a quantum correction to the muon mass 5 times larger than the standard model one. So we need, say, order 10% fine-tuning in muon Yukawa above this line. And this red shaded region is excluded by the precise measurement of the electric gauge boson with the standard model leptons because of this deviation. So but here I require choose a parameter so that the observed discrepancy of the muon G mass is explained from this new physics model. And so the lepton collider in Japan is a plant named International Linear Collider, ILC. So electron and positron collide with each other and produce a pair of W boson. By precisely measuring the decay pattern of the W boson, we can more precisely test this model. You can see that all parameter region can be covered by the International Linear Collider. And with a high luminosity LHC planned in the next decades, we can also probe this parameter region. So because of this surprising that naively leading correction to the muon anomalous magnetic moment vanishes, this model is easily accessible by the future colliders, near future colliders. Yeah, of course, this is about phenomenological implication, but it will be much more exciting if we have some similar surprise in a quantum correction to the Higgs mass. So, for example, in superstring theory, so we have one loop quantum correction to the Higgs mass. And if the scalar top mass is above 1 dB, the Higgs mass is obtained with a cancellation of the accuracy of 1%. So electric scale is fine-tuned with 1%, 0.01. 100 minus 99 equals 1, like that. But if somehow, with some similar mechanism, quantum correction to the Higgs mass can be suppressed by one more order, that 1% fine-tuning becomes no fine-tuning. So maybe it is interesting to think seriously about the possibility that Higgs mass is suppressed by a similar mechanism. Yeah, that I want to say today.